So my name is Alon. I'm the co-founder and CEO of Blue Cheetah Analog Design. I'll tell you some more about what we do as a company sort of throughout the presentation. But in terms of what I'll be speaking about from a technical and business standpoint is really all about how the emerging chiplet ecosystems can really enable optimized multi-vendor designs. So there's been a number of panels and discussions, and probably all of you here have heard a lot about chiplets over the last few years. And in fact, chiplets, very much have emerged as a key strategy for implementing sort of modern SoCs and really SiPs now. And that's really just primarily driven by the fact that, if we adopt a chiplet-based approach across a wide variety of different end application spaces, there's real cost benefits to be had by doing that. So one thing that is really worth kind of saying from the very beginning, because it'll somewhat highlight why some of the follow-on things that I'm going to be saying are going to be true, is that at the end of the day, manufacturing cost optimization is really the most well-proven and clear benefit of going with a chiplet-based approach. And the reason that I'm highlighting this here is that particularly if you look in the more sort of design automation, design efficiency crowd, a lot of the discussion around chiplets and particularly open chiplet markets is much more driven by the desire to have essentially reduced design cost and then essentially leveraging the fact that, okay, hey, like conceptually, I've built a chiplet, the thing works, like couldn't I just take that same chiplet and reuse it in other contexts, right? This is a very attractive proposition because it would appear then that we could reduce the overall design cost along with the manufacturing cost. As you'll see, and you can probably tell from my tone, that's the side of things that is a little bit more dubious. That's not to say that it can't be done, that's not to say that there aren't advantages there, but we probably have to chart a somewhat different path than what you might nominally first think of when you describe this type of chiplet scenario. And so again, this is sort of why I like to start out from just saying that, look, manufacturing cost being improved by chiplets is the proven thing. So in many ways, when we start thinking about this chiplet journey, we have to sort of almost take it as a constraint that if we're going to be building a chiplet, we can't be sacrificing manufacturing cost in favor of the design cost, because that's sort of going against what we've actually proven is really working and actually giving us a real benefit for sort of a hypothetical one. And for most engineering managers, that's a hard sell to make. So with that kind of context in mind, we really like to sort of think about just what is this overall chiplet sort of market striated into different use cases. So the one that absolutely exists today and has been out there for a while is what we refer to as the single vendor case, right? And so this is the Intels, AMDs, NVIDIAs, Marvells, and et cetera of the world, where essentially you control all sides. And typically speaking, this is really what I would refer to as an SoC die disaggregation case, where putatively there would have been one integrated monolithic chip that you would have built as a product. But typically for cost reasons, you figured out that this is not a viable approach to take. And so therefore, you're going to break the thing up into these different sub-chiplets, possibly use different process technologies for each one of them. But again, sort of you own the end product and you own all of the chiplets inside of the system. And so from a particularly die-to-die interface perspective, which perhaps I should have stated, Blue Cheetah is a die-to-die interface company, so that's why I will sometimes zoom in specifically on that part of the market. From a die-to-die interface perspective in particular, what you're going to care most about here is power, performance in area, and process portability. Because again, you own all sides, right? There's no interop or sort of reuse except with yourself. And so therefore, you're strongly motivated to optimize these things as heavily as you can for the more, let's say, measurable quantities that we're typically used to working with. All the way on the other side is what I'd refer to as the so-called plug-and-play market, right? And so the plug-and-play market is where this vision that I was referring to earlier sort of exists of, hey, I built a chiplet, I never coordinated with anybody else except perhaps by following a specification, and I had that chiplet and I could just magically take anybody else's chiplets and put them back together, and voila, I have new products that are sort of very fancy and good and better and so on and so forth. Okay, so again, you can probably tell from my tone that we're not really quite there yet, although I will give one actual real existing example of a plug-and-play chiplet that's out there today. Many of you could probably guess already which one it is. And if you're in this side of the world, it's not that you can completely throw out power, performance, and area or process portability. You often still times really will need a lot of configurability, because you can imagine even a plug-and-play world, different chiplets are doing different things, and therefore sort of even the die-to-die interface tends to need to be fairly configurable. But obviously, this is where interoperability from a multi-vendor and sort of with no prior coordination becomes sort of another very critical aspect. So To prefetch a little bit, although you can probably tell where I'm going, the medium here is what I'm going to refer to as a multi-vendor ecosystem. And in many ways, this is sort of the direction that things are actually going in practice, where the idea here is that we still actually have multiple organizations or companies involved, but it's not something where there's no coordination or pre-thought or pre-planning on the specific product market, the specific use cases, the specific even designs and specifications of the individual chiplets. It's just that there's things where groups of companies have realized that, okay, there is a strategic way that we can attack certain product markets together, and we can then define the chiplets that are obviously partitioned to the individual companies in a way that makes sense given their expertise, and then get those to actually be a viable and interesting product after the fact. So here again, you still care very much about power performance and area from a die-to-die interconnect perspective. You again care about process portability, just for simply being able to match the process technology to the individual functions of the chiplets. Again, you're going to care a lot about configurability for same reasons as we said in the plug and play. And you're probably going to want a standards-based design here, not necessarily so much because there is a particular standard that is doing exactly what you need it to do, but more so that you can essentially leverage all the commonality and all the common known techniques and not have to redesign everything from scratch every single time. So as I said, from a vision perspective, and this is really where much of the community has been paying a lot of its attention, plug and play appears to be a very, very attractive place to get to. And again, we're all pushing in that direction. The problem, of course, here is that it's actually very, very hard in practice to really do this for a whole wide variety of reasons that I'm going to touch on a little bit more here. But again, plug and play is sort of like, especially if you're a smaller startup company, it's really, really attractive, right? Because you say, oh, hell, look, I'll go and build one chiplet, and this chiplet will be used in all these different markets by all these different players, and look, this is amazing. I can save all my NRE costs, and it's just magic, right? Well, as with most magic, once you pull open the hood, most likely it's not working the way that as it's first described. And so that's where remember I said before I was going to point to one existing example? Well, the one existing example of a plug-and-play chiplet is HBM, right? It's actually a very successful example these days. But there's a few, sort of caveats or important factors we have to consider that are really sort of what enabled HBM to become successful in this way. The first is that it's supplied by vendors that effectively are used to, and not only used to, but are successful in competing in commodity markets with very, very tightly and functionally, electrically, mechanically specified parts, right? There is a very, very concrete size, footprint, bump out, power profile, functional profile, and so on and so forth for an HBM die. And you can go and buy that from 3 to 4 vendors today, right? Or in principle, you can swap them all out, and that's actually indeed mostly true. But again, it's not that you just took something and you drew this box and okay, this box fit here, right? It is a very, very detailed and specified thing, and you must build to that spec to have the hope of the chiplets to actually work together. So the challenge here is that if you're now going to try and apply this same model to a logic chiplet, you have to realize that logic tends to be functionally much more diverse and much more complex than memories. That's not a knock on memories. They're wonderful products. They're very, very important, very sort of innovative. It's just a characteristic of these types of designs. And so that means that we now have to sort of take the same level of detailed specification and apply it on something even more complicated and really sort of target it very concretely to particular products and use markets. Because again, if we don't, it's unlikely that things will actually plug together and really work the way we expect them to. And so this is really sort of, again, starting out as a smaller company where, it can be the attractiveness of this plug-and-play model can kind of get you into trouble, right? Because you can sort of start out saying to yourself, okay, well, I'm going to try and build this chiplet with this concrete set of specs, but I'm going to try and do it with 3 or 4 different end products and markets in mind. And then you sort of get into this loop of, oh, well, if I want to be in that market, I have to do this thing differently. And if I want to be in that market, I have to do that. And oh, that socket is going to look differently than this one. And so obviously, as you guys probably all recognize, from anyone who's done any real engineering work, you get in this sort of infinite loop of definition and attempt to execute and then redefine and re-execute. And these things very rarely converge the way you'd like them to, right? With at least 1 or 2 axes of time, cost, performance, whatever it is, pushing out well beyond usually what's acceptable. So this is not a doom and gloom talk here, right? The point is not to say that chiplets are never going to work. The point is we just really need to be approaching this problem a little bit differently than what I think we by default tend to think about. And so in particular, as I mentioned before, multi-vendor ecosystems, which actually are really emerging already today, but I think will become prevalent over the next few years. That's kind of the way that you sort of detangle all of these complex business and technical challenges that I was referring to before. Where what you basically says, okay, look, let's get an ecosystem of companies together. Again, 2, 3, 4, 5, whatever happens to logically make sense for that particular type of end application or product family. Define the chiplets to the sweet spots of the actual end product we're attempting to go after. Also, obviously, matching the particular capabilities and expertise of the companies involved in the ecosystem. And then now, once you've done that, you can actually define a concrete and real spec that everyone can go and build to, right? It's an internal specification, and that it's only something you're using to coordinate between the multiple partners and to figure out the behavior of the end product and the attractiveness of the end product. But it's not sort of this nebulous thing that you're trying to figure out just what to even do in the first place. You now have a concrete target. And so the point here is that that's not to say that we will not actually be able to use chiplets in many different markets. We absolutely will. It's just that there may be different, let's say, chiplet sockets that even though I may label them as something like a GPU socket or an I/O socket or something like this, if you look at them being applied in different end use cases, their actual functional, mechanical, and electrical characteristics may be very different, right? So the I/O socket, sort of in, let's say, the automotive context, may be very different than in the high-end compute context, may be very different than the consumer electronics context, and so on and so forth. And so another, I think, really important point here is that, at the end of the day, once sort of, these ecosystems have become successful, right, and are starting to make enough, essentially, revenue, by a dollar's perspective, then you have an opportunity to sort of open these things up and say, okay, you know what? We really do need multiple vendors for, say, whatever, the GPU socket in, the automotive marketplace. So we're going to release, sort of specifications on what that chiplet actually needs to be. And if there's enough volume, meaning, again, dollars behind, sort of the chiplet that could plug into that socket, that will incentivize people to then go and actually build those things because they know, hey, there's an actual customer, there's real revenue that I can unlock from having invested all this effort in building this thing in the first place. And so much like many other, sort of markets, this will be the type of thing where, the first people that get there and are successful will likely define the path forward for everyone else because now, they'll have the concrete target to actually go after. So as I said, Blue Cheetah and I personally am really sort of, a dot-to-die interconnect and sort of phi type of person. And so I want to sort of springboard from this to say a little bit more about, just what does all this imply about how you actually now have to build the interconnects to be able to work in all these different application spaces. And many of you are probably familiar, there are a number of dot-to-die standards that are out there, both UCIe and bunch of wires being kind of the most prevalent ones today. But in a sense, this is really digging one more layer under the hood of saying, well, look, yeah, there is a standard and there's sort of a set of specifications one can look at. But if you really look at how these things are actually built and implemented, depending upon the real application and usage, even down in the guts of the phi circuitry, you tend to build things in a pretty different way. So from that standpoint, we like to look at basically 4 different categories of dot-to-die interconnect phis in particular that are sort of striated by package type. The sort of bandwidth per wire that you're running them at, the actual interface reach, meaning how long, how far apart can you put those chiplets and how things work, and therefore the energy efficiency of those solutions. So the first category is going to refer to as a so-called ultra-wide type of interface. These are typically used in things like FPGAs were sort of probably the first introduction of this. There's a number of other more bespoke type of applications that have used these as well. And the idea here is that you're typically or almost strictly on an advanced package technology where you have very tight density of essentially bumps or interconnects available to you to just get a large number of wires from one chiplet to the next. And because you have a large number of wires available and or you don't have a very stringent bandwidth density constraint, that means you can run the actual I/O interfaces at a relatively low data rate, something like 8 gigabits per second or lower. And this means also the range is therefore usually fairly constrained because usually in these more advanced, sort of thin metal lines, the resistance is large, so you can't actually signal very long distances. But you can make the things very, very energy efficient, less than about 0.3 picojoules per bit, sometimes even approaching about 0.2 picojoules per bit. So this is kind of like as close to on-chip wires as you're going to get, right? On-chip wires, you don't run them very fast. You just have a whole bunch of them, and you just have really, really simple circuits that are essentially driving and receiving them. This is kind of the closest cousin of that. The next category we like to think of as what I refer to as ultra-dense. And this is really in your like AI accelerator, data center GPU, and so on and so forth, where you're really trying to get the absolute highest end of bandwidth density, meaning how many terabits per second can you escape out of a die within a certain amount of shoreline. These are, again, basically advanced package only, but the big differentiation here is that you're going to run these things at much, much higher data rates. So all the way up into the like 32 gigabits per second or so. And when you have these kinds of things, you can really absolutely get things like 10 plus terabits per second per millimeter of shoreline, which is actually starting to get very close, if not even sort of slightly above what some of the on-die bandwidth densities may be. But the thing you have to keep in mind here is that now, because these circuits have to run actually at much, much higher rates, you're going to have to pay somewhat of an energy penalty, because you can't just sort of can't just be a really simple inverter and driver and receiver. It's got to actually be sort of having good jitter, good performance, low thermal noise, so on and so forth. And so that means that you can't really scale the pitch of these IOs below a certain level, whether it's really 45 microns or 35 microns, again, somewhat variability, depending on the exact process technology. But to zero order, you're not going to go below some level simply because of the fact that the circuits themselves can't be squeezed down any further in order to meet this level of performance. And so again, it's going to sort of limit kind of the area of the IO solution. It's also going to somewhat limit the energy efficiency. So you're probably now in the 0.3 to 0.5 picojoules per bit. But this does get you sort of the absolute highest end of the bandwidth density. The other two categories are both sort of some variant of what I'm referring to as full reach. And what I mean by full reach here is that something that you can actually basically physically place things as far apart on the package as is likely practical, so somewhere around 25 millimeters or so. But the interconnect actually supports having that full amount of data rate and bandwidth even at that full reach of distance. You might be thinking to yourself, oh, hey, but like chiplets, I've always seen pictures of like everything just snapping together perfectly, right? Well, sometimes in practice, it doesn't quite work out that way. And sometimes if you're quote unquote unlucky, it means that you actually have to go like all the way across one die to get to another one. That's where these types of 25 millimeter types of reach start to become interesting. There's other cases you can think of where you're like trying to get from one side of one die to the other of another one, even if it looks like a linear line. Again, these are the types of cases where having that reach actually turns out to be very important. In order to get those kinds of reaches, you tend to need thicker metal wires. So that means you're typically on a standard or fan-out type of package. You're going to run these probably up to about 40 gigabits per second or so. As technically you can go above that, but you're probably not going to go too much above that for energy efficiency and area reasons. And as I said, because you're now sort of doing something that really has to have these longer reach, it tends to be a more challenging signaling environment. The circuits tend to need higher performance. And so again, you're probably in the 0.4 to 1 picojoules per bit range. Finally, there's sort of what I'll refer to as the cost-optimized full reach. And in this category of applications, basically this is the style of applications where it's typically like industrial or consumer, where costs are very, very critical. And so because of this, you have to have basically a very small number of layers of metal in the package. If you have a small number of layers of metal in the package, that restricts basically how much bandwidth density you can get out of these interfaces. And so you end up having to modify the PHY circuitry really to meet those particular requirements. Because again, it's pretty different than sort of saying, well, hey, I've got like 8 layers of metal up in the package that I can use all for my signaling purposes. So I'm getting sort of towards the end here, and what is it that having all done this entire setup, what is it that Blue Cheetah actually does? Well, we deliver customized chiplet interfaces, because as you've hopefully noticed from sort of the whole slant of this talk, there is no one size fits all, right? There's a lot of different places that chiplets can go, depending upon how they are used and which packages they're in and so on and so forth. That can really drive the design of the interconnect in a fairly significantly different way. Since I'm here at DAC, I'll sort of throw out the brief mention of it. The way we sort of deliver these customized interfaces and the way we can do this in a essentially efficient manner from a both time and cost perspective is by leveraging what we refer to as a generator-based design methodology. Generators basically in this context just means that we've taken our design expertise and programmatically codified the way in which we approach particular designs, so that when we then get a request of a particular customization or a process port, we can simply re-execute that programmatic generator rather than having sort of our army of human laborers sort of actually get the design back out the door for that specific set of constraints. So we've been quite successful in leveraging this generator-based approach to address and essentially deliver to our customers customized data interconnects that really cover this entire range of use cases that I just talked about before. The way that we've sort of realized much of this trend in this multi-vendor ecosystems is that fortunately we've been very lucky to actually partner with many of the leaders that are developing these multi-vendor ecosystems and are really sort of trailblazing in that direction right now already. So just to sort of wrap up quickly, as a reminder, cost, whether it was manufacturing or design, but really primarily, sort of a requirement is cost, is the reason you end up building a chiplet, right? That was the whole motivation behind this. That's why you sort of move in that direction. And so the thing we have to keep in mind is that, if we're going to keep that manufacturing cost, sort of as being something that, we can't sacrifice on, we really have to realize that we're going to be customizing and optimizing every chiplet that we build for the specific use cases and for the specific markets it's going to end up being utilized in. And so once that's true, obviously what you focus on in terms of the design of both the chiplet and the interconnect then gets modulated quite heavily as well. So as I said, you're unlikely to find sort of a one-size-fits-all solution for chiplets. You really have to define a specific product or a specific market that you're going after with what I would refer to as a chiplet socket. Where again, a chiplet socket is something that's it's a very, very concretely, functionally, mechanically, electrically, thermally, et cetera, sort of specified thing in a given product, in a given market. Again, much like a la HBM. But once you've defined those things, again, multi-vendor ecosystems that sort of have collaboratively defined what those sockets are, and essentially open those things up so that people can actually go and design to them, that's really the way forward, right? That's how we're going to be able to sort of break this conundrum between we want to be able to reuse the chiplets, but we really have to customize them for an individual particular use case. So as I said, Blue Cheetah, we work very closely with our partners and our customers so that at the end of the day, once you've gone through that whole difficult process of deciding, well, what's the chiplet we're actually going to build, we can deliver the interconnect that will solve that particular product for you, right? So that will no longer be the bottleneck or the limitation. So you won't sort of find yourself saying, oh, well, I really wanted this interconnect for this product. That's where we come in, and that's where we'll work with you to make that happen. So thank you very much all for your attention. I'm very happy to take any questions if there are.
I wondered if you could comment on the state of the tool flow for putting chiplet systems together.
Okay, so the question was, what's the state of the tool flow for putting chiplet systems together? There is a lot of work and a lot of activity of people trying to make the tools, sort of get to the point where this is a much easier thing to do. I don't think I'll be offending anyone by saying that there's clearly a lot more work to be done there, across the full broad, across the entire range of sort of activities, right? Whether that's in the packaging side, whether that's in the verification side, whether that's in the simulation side. There's a lot of work for us left to be done. I think the answer or the good news is that people have figured out ways to get these things out the door. That doesn't mean it's the most efficient. That doesn't mean it's the way it should be. But at least there are sets of flows that people can follow and will get things working. But absolutely, I think that's a big thrust. And many of the folks here in the booths are working on products of various forms and shapes to try and tackle different pieces of that overall chiplet design problem.
In one of your first slides, you talked about standards. And it seems to me like if you're in the process of building customized interfaces between chips, that standards is kind of contrary to your business model.
It's a great question. So if you recall, at some point fairly early on, I had said that you want things to be standards-based, so there's kind of a common baseline of things that you can build on top of and really focus on where it is you're differentiating. That's sort of the way to resolve the potential conflict that I think you're asking about in terms of even our business model, and that all of our solutions are standards-based, but we then build and modify from that accordingly based on the individual needs of the customers. So for example, if there's something where we realize that, okay, hey, we can't follow exactly what the bunch of wire spec says in this subsection, blah, 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 because it's going to mess up the customer's product. Well, we say, okay, fine, we're not going to follow that, right? We'll do what we need to do. But everything else can be built on sort of somewhat of a more standard platform. And to be frank, you need some baseline, let's say, assumptions. Because when I say customization, I don't mean we're going to do anything for anybody. But we're going to do things that sort of make sense and are sort of practical and obviously will be sufficiently compensated for actually customizing in that particular way. Because if it's something where I have to reinvent it every single time, right, I don't get to use the generator, right? I don't get to use my known methodology. I have to reinvent it, and that's expensive for everybody. So that's the way sort of that particular conundrum works out. Is that customized doesn't mean completely against any standard. It just means you move the things that you actually need to move and are critical for the particular, let's say, use cases that you're interested in. But it's a great question, a great observation.